That's better. Okay, so thanks all. I'm Jens van der Plas, and I will present result invalidation for incremental modular analysis. So let's look first at an example workflow flow containing a static analysis. So a program P gets analyzed by an analysis, and you get the result R, and then you update the program, and you analyze it again, and you get another result. Of course, often these updates are very small, and entirely reanalyzing the program is actually probably a waste of resources. And to speed up the analysis, we can adjust the workflow to use an incremental analysis. And based on program changes, an incremental analysis will just update previous analysis result. You can't really hear it when I do it like this. So. Okay, sure. Okay, so can you hear it? Okay, so to speed up the analysis, you can actually adjust the workflow to use an incremental analysis. And based on the program changes, an incremental analysis updates the prior result rather than entirely recomputing it. And doing so, you will actually only update a part of the result that was affected by the changes, and this, of course, saves you some valuable time. And this reduction of the analysis time will then allow it to use the analysis, for example, in an IDE or CI pipeline, exactly where developers actually need these results. Now, existing work on incremental static analysis actually has some drawbacks. For example, it's targeted to specific analysis like data analysis. It might need to revisit every program point, which is something we want to avoid, of course, especially for big programs. And third, some frameworks actually require you to entirely re-implement your analysis in a specific format. A more ideal solution would be to have a structured method to make an existing analysis incremental. And in our previous work, we already introduced the basic approach to incrementalize an effect-driven modular analysis. However, our approach actually caused a big loss in precision, which we will remedy in this work. Now, let's recap what an effect-driven modular analysis is. It's actually a variant on modular abstract interpretation as introduced by Cousteau and Cousteau. It computes interprocedural control and data flow properties, and it's actually applicable to highly dynamic programs without a static call graph. And a modular analysis that cuts a program into chunks, and which we call modules, and analyzes the runtime instances of these modules in isolation. As for example, in the function modular, you divide your program into functions, and you analyze function calls in isolation. And we call the reification of these function calls in the analysis components. Now, every component may depend on or change a part of the global analysis state, in this case, the global store. And this means that components are actually interdependent. Now, an effect-driven analysis tracks these dependencies and using effects and uses these to drive the analysis. But importantly, the reification of these components and effects that enables incrementality. Now, an effect-driven analysis actually consists out of two phases. We show here the inter-component analysis, which actually is a worklist algorithm that schedules components for analysis based on the effects that were emitted. And then one component is analyzed by an intra-component analysis, which emits those effects. I will just give an example on how this works using a modular analysis with a type domain of this simple program where we define a variable x, we define a function that calls another function returning x, we define inc, which increases x and returns true, and then we call just fun. So initially, your worklist contains like a main component, which we have the orange squares for, and that actually represents the entry point of the program. And your global store maps every value to bottom. So when we analyze the main component, many things happen. So first, you define x. So that means that you write x in the store, generating a write effect. And these addresses are actually in the store are these blue circles you see. And then main encounters the call to fun. But what it does not step into the function, but rather it creates a call effect. and a component. Given that this component is new, we add it to the work list as well. And we, instead of calling it, we read the return value of fun from the store, which yet is still bottom. Then main will write its own return value to a dedicated address in the store and terminates. So after analyzing main, what will we do? We will analyze fun. And during the analysis of fun, we again encounter a new component, namely ink. So we create a new component, add it to the work list, read the return value, which is still bottom. When we read this value, we generate a read effect. And this read effect actually indicates a dependency on this value. So we say that fun is now dependent on the return value of ink, similarly as main is dependent on the return value of fun. And then what fun does, it reads x, generating a read effect, which is arrow, and writes to its return value in the store, generating a write effect. And of course, as main previously emitted a read effect on this address, and thus as a dependency, we re-add main to the work list, so it can take into account the updates to this value. Now, let's assume ink is analyzed next. During the analysis of ink, x is read and written, so we generate a read effect. However, as x is not updated in the store, it remains an integer. We do not generate a write effect since no dependent components need to be reanalyzed. However, fun is added to the work list as the return value of ink is updated. So I guess you get a bit of feeling on how this works, and the analysis continues actually until the work list is empty, which means that the fixed point has been reached. Our result actually consists out of three parts. First of all, the components, which are the orange squares. Then the dependencies, which are the read effects. And of course, the global store, which are our values. And so our previous work on making such an analysis incremental actually consists of two steps. In the first step, we perform a change impact calculation that detects all components that are immediately affected by a change, and we add them to the work list. And in the second step, we just restart the fixed point computation of the analysis. And we express changes to programs with like a change annotation. So this is the old expression x, which is replaced by a new expression, in this case, equals x1. And when we evaluate this previous work against some quality criteria, we see that it's perfectly sound, so it has a perfect recall. It also results in significantly faster analysis times. However, what is less promising on this work is that it's quite imprecise because it only has monotonous updates. And thus this means that actually the result of your analysis will not only over-approximate the result of your current program version, but also of all previous program versions. And of course, this imprecision sits in the various parts of the result. You may have components that no longer correspond to program behavior, similar for dependencies, and your values in the store may be imprecise. And this imprecision can spread from one part to another. For example, if your store is not sufficiently precise, you may explore too many paths in the analysis, generating too many components. And so we developed in this work a result invalidation strategy for each part of the analysis result, so that we can actually remove these outdated results. Now, generally, what does an incremental analysis do? It has a two-step approach. So first, it invalidates, and that means it over-approximates and removes all results that are invalidated or outdated. And then it does a recomputation step, which means it will restart the computation and for new information. However, as we have to over-approximate during invalidation, we may actually remove way too much information, which means we have to recompute that information, the same information during the recomputation phase. This is a bit of a waste. And therefore, in my approach, to actually avoid this over-approximation, we actually start to interleave recomputation with invalidation. So after every analysis of a component, we try to invalidate information. So recomputation, you can say that it triggers invalidation, and information is only removed when it's no longer inferred by the analysis of any component. So I said we have three strategies. The first strategy simply is component invalidation, and actually it just removes components that no longer correspond to a program behavior. So suppose you have this little program on the left where you have a factorial function, which is called in a loop using fac loop and the loop functions. Now, if you update this little program to call fac immediately instead of fac loop, then of course fac loop and loop will no longer be called. And in this case, we actually have to transitively check the liveness of components because, for example, the removal of fac loop will also need to cause the removal of loop. And for this step, we can rely on the call effects that were emitted during the analysis. Similarly, for dependency invalidation, we just remove dependencies that are outdated, and removing the dependencies does not only improve the precision of the analysis, but also its runtime because it avoids spurious reanalysis of components. So again, small example, suppose we have a little program with two variables x and y, and we have a function that returns 1. If we now change the function to return y instead of x, then we can remove this dependency on x. And so after the analysis of a component, we apply component and dependency invalidation, which takes into account the information just inferred by that analysis. And to do so, we actually compare the effects that were inferred by the analysis of the component to the effects that were inferred by its previous analysis. And if any effects or information is removed, we can delete the corresponding results from the analysis result. And like I said, when a call effect is removed, you have to transitively check all the liveness of all components because other components may still create a component, or you have to remove multiple components. Now, actually, the most important and most interesting strategy is write invalidation. And write invalidation will allow for non-monotonic updates to the value store, which stores values that are, of course, part of a lattice. And normally, as values are joined and written to the store, the analysis loses track of its constituents of these values. And for this reason, we actually have introduced provenance tracking. And for each value, we register the contribution of each component. And on the figure, you see this in the little pink. It's not very readable. I'm very sorry for that. But you can see, for example, that main contributes integer to y. Having this provenance information will allow us to perform non-monotonic updates to the value store. So consider, for example, this little program where you have an identity function that is called with a boolean and an integer respectively by the functions f and g. So in the value store, these values just get joined. So you know x can be an integer or a boolean, but that's all you know. But with provenance tracking, you can see that actually f contributed a boolean to x and g contributed integer to x. And suppose we now update this program so that f no longer writes a boolean, no longer calls the identity function with a boolean, but also with an integer instead. So what would a monotonic update do? It will just join the value written by f with the value that is already in the store. So you keep int and boolean, and actually you can not invalidate this boolean value, which yields imprecision. However, with provenance tracking, you can actually see that this contribution from f to x has been updated in a non-monotonic way, from bool to int. And then we can use the provenance and join the provenance together to compute a new, more precise value for x in the store. So we can update x just to be int now. And as the value of x has changed, the effect-driven analysis will also cause the identity function to be reanalyzed because it has a dependency on x. And again, provenance tracking and these effects will cause a non-monotonic update of its return value. So actually you can see that using this scheme, this can be propagated now. So the update can be propagated. And then we can have further invalidation. So actually the entire store can become more precise. Now, we actually distinguish two cases for write invalidation. So when a component no longer writes to an address, we can use all provenance, join it together, and compute a new, more precise value. And in the other case, when the update happens and it's non-monotonic, we can use the provenance to also have a non-monotonic update. And in each case, the changes can be propagated to other addresses as well. But what is interesting is that write invalidation can also be applied upon component deletion. So when you remove a component, you can just retract everything that it has written from the store. So all these addresses can become more precise as well. So we can actually say that write invalidation can reinforce component invalidation. Now, we have evaluated this on three criteria. The precision compared to an incremental update without invalidation. We have looked at the analysis times. So how does it relate to an update without invalidation? Does our strategy make the update slower? And of course, how does it compare to the time it needed for a full program analysis? Because that's of course the goal, that we are still real faster. And we created two benchmark suits for that, like a small curated suit with real-world programs and changes, and the small curated suite, we manually added these changes to reflect real-world changes. And we also have a larger suite where for each of 190 programs we generated 5 mutations, and here the changes come actually from various edit patterns. And an example of a curated benchmark, this is a p-val benchmark. So what we did, we just introduced a new abstraction for tagged list, and then we used it alongside in the entire benchmark everywhere possible. So this is a benchmark of like 644 lines in which 38 changes were made. So to evaluate the precision, we look at the percentages of the addresses in the value store of an incremental analysis after its update that actually match the values in the store of a full reanalysis. So that's when they're fully precise. And we plotted this for all curated benchmarks, and of course we used the geometric mean here on the right for the generated benchmarks. And we see actually that for some benchmarks, write invalidation significantly improves the precision of the store, although it's not fully precise yet for all benchmarks. And we see that for the generated benchmarks, approximately 50 to 20% of addresses now is fully precise, which is of course a significant improvement. And also we see that, for example, for flip loop and the generated benchmarks, reinforcing the component invalidation with write invalidation yields some additional benchmarks. So although we're not yet fully precise, write invalidation significantly improves the precision of some benchmarks, and even more so when applied together with component invalidation. And then to see whether our strategies have an impact on the speed of an incremental update, we compared the times taken by an update with a strategy to a time taken by an update without a strategy. It's plotted relatively here. And we omitted dependency invalidation. And actually we found that component invalidation and dependency invalidation have no significant impact on the analysis time of an update. However, write invalidation does have an impact. And why is this the case? Of course, because write invalidation will fiddle with the store, and when addresses get a new value, it might cause components to be reanalyzed again. So it will trigger reanalysis. So as write invalidation may cause the reanalysis of components, it does have an impact on an incremental update. And then we also compared the time needed by an incremental update to the time needed by full reanalysis of the program. And for the curated benchmarks, we see that our incremental update is still about 5 times faster than the full program analysis. The same easy story is not applicable to the generated benchmarks. We found that in some benchmarks, actually changes may remove a lot of program behavior or have a significant influence on the behavior of the program. And we discovered this by looking at the analysis time. when a full reanalysis of the updated program is a lot shorter, for example, than the full reanalysis of your initial program, then a lot has changed. And in these cases, you cannot expect an incremental analysis to perform well, which you can see on the graph on the left, where we have slowdowns of a factor 100, even to a factor 1000. And that's, of course, because you have to invalidate and recompute, whereas a full update may just recompute and doesn't have to invalidate. However, in other cases, we see that we're overall still quite a lot faster than a full analysis of the program, which is, of course, promising. So overall, an update is faster than a full program analysis, but you cannot expect it to be faster in all cases. So to sum up, we have introduced 3 techniques to improve the precision of our previous incrementalization strategy for effective modular analysis. And we make use of reified components and dependencies, and of course our interleaving principle to invalidate results. Overall, we see a precision improvement, and we are faster than a full program analysis. So that's it. Thank you for listening.
Any questions? So while you are probably thinking, I have one. So you compared execution time. What about memory consumption? Did it change or not? And more precisely, in certain cases, I can imagine of implementing analysis in a way where you don't save, where you try not to save many pieces of data, many invariants, and probably do not carry very much. And that would make it a lot harder to implement such techniques. So did you consider such questions?
I did not yet evaluate it on memory. It's also an important thing, of course, as incremental analysis often use a lot of caches. However, I don't remember by heart, but I don't think we gave the GVM a lot of memory when running the experiments. So I don't have a clear answer on that because I didn't evaluate it, but I don't think it's tremendous amount of increase.
Okay, thank you. Fair enough. Any other question? Yeah, Michael.
If I understood correctly, your interleaving principle that as soon as if I invalidate one procedure and recompute its results, and if I get different results, then I would have to propagate that to callers. Is that pretty accurate?
Well, not only to callers, because I mean, you can have shared data structures, etc. So,
right.
And also higher order functions, etc.
Sure.
So what actually the interleaving principle does is you analyze a component and you actually compare its results to what you got from its previous analysis. And you, for example, find, oh, it's no longer calling these other functions, it's no longer writing these things to the store. Then you will look at what is dependent on these things and reanalyze it.
Yeah, okay, so that's my understanding. So then with that understanding, I wonder how things work in the recursive case where I might kind of have to come back to the same component eventually.
We support recursive functions, etc. That's no problem. We are not yet fully precise, however, and that becomes also values may be recursive. So due to abstraction, values may depend on itself for its computation, and this is something we cannot yet handle. But recursive functions, higher order functions, that is all supported.
Do you know, for instance, that are you still guaranteed to terminate to a fixed point? You're not going to alternate back and forth or something like that?
You're referring to that we cannot go up and down, or?
I guess the potential, devil's advocate here is maybe if I update the results I've computed for one function and then propagate them around, and eventually I invalidate, based on a callee, I invalidate again the results for this function and have to somehow recompute them again. Can that happen?
I don't think it cannot cycle on forever, definitely, because when you infer new information, you will never invalidate it again. And when you remove information, it might be reinferred because it was introduced somewhere else, but then it will stay there. So you cannot have an infinite analysis normally. So termination is guaranteed.
Okay. Any online questions or any other questions? So actually, I may have some more. So if you in this recomputation and invalidation system, can you kind of spell out what are the requirements you put on the abstract domains that you are using? Like, can we implement this for arbitrary abstract domains without changing too much the inner parts of the abstract domain? Can you make it a high-level interface that is?
Well, you certainly cannot have like this infinite ascending change in your domains. But apart from that, if I think there is not a bit of problems. I mean, I did it now for a type domain. I also have an implementation for another domain in my implementation. So as long as you're guaranteed to reach a top value at a certain time, then I think you should be fine.
And if you wanted to support domains with infinite chains, even though we may not have optimal like minimization of the amount of recomputation work, do you see a way of going this direction?
So if you want to support
infinite chain domains, but probably at the cost of not quite getting as good results as you could get here, just because we do extend the setup.
I think there might be with widening and stuff you can certainly get around. Actually, what I present is like an incrementalization approach for a modular analysis. So I think if your original modular analysis would terminate, then this should not actually change your termination.
Right. So that means that you just would also be able to support some analysis with widening and infinite chains.
Yes.
Probably with worse results, but I mean that cannot be avoided.
Normally, yes. I haven't tried it, but I think there should. I don't see any reason why it should not work.
Okay, cool. Okay, so any last question? Sure, please go ahead.
In the beginning, you refer the abstract semantics dependency by the causal, and in that work, the dependency he didn't catch the implicit like channel dependency in that work. Is your incremental analysis able to catch the implicit channel dependency?
You mean like control flow?
Yes, both control flow and data flow. If it's a variation in two words.
Well, actually, your control flow dependencies are actually also your call effects actually are control flow. Within components, I don't think it's needed because it's function modular, so you don't have to grasp everything with every if statement. As long as you know which function calls which other function, I think you are fine with that.
Okay.